Hi, this is my Lab 4 video report on strings and oscillation. So a little table of contents up here. So we're going to go through the objective of the lab, the content of the lab, the K, the spring constant, and the relaxed length calculations, tracker data, some of the coding, then we're going to go through the simulation and glow script, and then finally, what does this mean? So the objectives of this lab are to observe the motion of the spring mass system, and while observing that motion, we want to apply Newton's second law and the energy principles to analyze the changes to the system. So some contents, we have the position update formula, final position equals initial position plus average velocity times delta t. Velocity update formula, final velocity equals initial velocity plus f net over m times delta t. The kinetic energy formula, 1/2 mass times velocity squared. The gravitational potential energy formula, mass times the gravitational constant times delta h, which is height. The potential spring energy formula, which is 1/2 times the spring constant times S, which is the length of the spring minus the relaxed length of the spring squared. Have the K and the L naught calculations, K being the spring constant, L naught being the relaxed length of the string. So K is equal to 4 pi squared times mass over T squared, T being the period, and we calculated the period by taking time that it takes to go through 3 periods on the sinusoidal graph over on the right. So the time it takes to do 3 periods is 4.952 seconds. Divide that by 3, you get 1.65 seconds per period. So the mass of the ball on the spring is 4.402 kilograms. The period is 1.65, obviously. So we get that K is equal to 5.82. And then L naught is equal to L, which is the length of the spring, minus mg over K. So mass again, 0.402 kilograms. G is equal to 9.8 meters per second squared. K, like we calculated before, 5.82. L is the length of the string, the initial length of the string, and that is 0.7 meters. So then when we plug all that in, we get that L naught is 0.023 meters. As you can see here on the tracker video, the mass is oscillating in a circular motion, and this is because of the work done by the spring force on the mass. And as you can also see, the x and the y values are moving in a sinusoidal function, so they're going up and down over and over again. And these are also inverses of each other. That we put in the glow script to run the simulation. So a lot of this is just initial conditions. So we have the mass of the ball, which is 0.402 kilograms. We have the initial position of the ball, which is the position at time equals 0. We have the gravitational constant, 9.8 meters per second squared, the calculated spring constant, which is 5.82, the L naught value, which is 0.023, which is also a calculated value. Then we have the code for the length of the spring. We have the calculations for L hat, the calculations for S, which is equal to the magnitude of L minus L naught. And then we have the 4 energies. So we have kinetic energy, which is 1/2 mv squared, gravitational energy, which is mg delta h, so that's delta h being height. As spring potential energy, which is 1/2 ks squared, s also being the magnitude of the length minus L naught. And then we have total energy, which is E equals K plus EG plus US, so that's total energy equals kinetic energy plus gravitational potential plus spring potential. Coding we put in the glow script. So this is the loop. So while time is less than 9.429, which is the total time of oscillation on tracker, we have this loop. So we have the initial energy is located on top. And then we have the gravitational force vector, which is the negative mass of the ball times g, which is the gravitational constant. We have the spring force, which is negative k times s times L hat. We have the net force, which is the gravitational force plus the spring force. Then we have the velocity update formula, which is final velocity equals initial velocity plus F net over the mass of the ball times delta t. We have the position update formula, which is position of the ball equals initial position of the ball plus velocity times delta t. And then we have the spring update code, so that's going to be updating the location of the spring as time goes on. And then the change in energy code is going to be updating the change in energy as time goes on. So as we can see here with our simulation on glow script, so the blue is the delta K, which is the change of kinetic energy. The red is the potential energy of gravity. The green, the potential energy of the spring. And as you can see, all those are sinusoidal graphs, and they're going up and down while the total energy stays at 0, and that's because of the conservation of energy. And then again, you can also see the graph of energy versus time over there, this time in picture format. So what does this mean? Yes, the energy principle is followed. The total energy is conserved, so it's always at 0, while the components of energy change, so delta K, delta U grav, and delta U spring, all those can change, but the sum is all equal to 0 altogether.